Hello, Professor. How are you?
Hey, I'm good. How are you?
Fine, thank you. How's your week going so far?
Mm, Good. I mean, it's just a bit hectic. There are a couple of deadlines. Yeah,
Yeah, it's the same for us. Just rhyming day in day out.
exactly. Yeah, I mean, learning never stops. It's just when you become a professor, the deadlines are just different deadlines. So instead of midterms, now you have deadlines for your proposals, papers.
Is that what you always wanted to do? Always wanted to be a professor? Never wanted to go into industry or
Uh, that's so no. Like when I joined masters, it was I wanted to just get an engineering job and uh, and be like regular software engineer, right? That was my dream. That was my dream always. But during my masters, I I worked under this professor called Mayur Nayak. Like he was very good. Uh, and unfortunately, I was working with some PhD student. The PhD student left, so I had to finish his project by myself. That's when I got hooked into research. I was like, okay, this is the thing I want to do, and yeah, rest all is history.
that's awesome. Thank you so much for sharing that with us, Professor.
Cool. So how is the lab 3 going? I saw a couple of students who came to office hours. It was interesting to see the kind of bugs or like issues that you were facing. So how is lab 3 like going? Like, do you guys have any issues with lab 3? Question one, like so what which question you guys are working on? Just type the number. Which question in lab 3 you are working on? See, see, good. So question 2, question 3. Question 2 to 3, very good. And yes, yeah, Carrie, there was a very interesting issue in today's lecture hours where I think one of the students, we were trying to debug like using of condition variables to signal when the message, like when the message box is empty and when the message box is full. And we couldn't figure out exactly what was happening. I thought about it a bit, and then I realized that if you're using, if at all, if you're using condition variables to signal receivers and senders, make sure that you always signal the signal function. Make sure that you always signal the condition variable. Okay, don't signal when the queue is empty or when the queue is full, but the signal should always be done. Okay. However, you can, but you have to wait only if the condition is not met. Whereas when you are signaling, you just signal. You always signal. Okay. So if you're not using condition variables, then it's fine. If you're just using logs, it's okay too. If you're using semaphores and logs, that's fine too. So yeah, if you're using condition variables, just make sure that you always signal. Okay.
Professor, we got it to work using semaphores.
Oh, okay.
Yeah.
Perfect. Okay. Yeah, that's nice. Mm, Okay, now, okay, let's get into today's class. Today's class is interesting. So we have we have looked into page fault handling in the last lecture, where we saw like how when a page fault happens, how operating system brings the required page into physical memory, and how it updates the page table entry of the process which needed the page, right? And in order to maintain the association between physical page and the corresponding process to which the physical page is assigned, so we can use inverted page table. Okay, few things like virtual address and virtual memory are related concepts, but one distinction is you can have virtual address without virtual memory. Okay, that means you can operating system can provide you an abstraction of virtual address without doing any demand paging or demand segmentation, nothing. Okay, whereas virtual memory, in order to enable virtual memory, operating system should provide both virtual address and also it should have a way to do the demand paging thing. Because virtual memory, by providing virtual memory, what operating system is saying to each process is like each process will always see fixed memory, like fixed memory size. Every process sees 3 GB of memory. However, operating system needs to multiplex all the virtual addresses, all the virtual memory into one physical memory, right? So the physical memory that you have may not be what virtual memory size is. So operating system needs to do the multiplexing. Okay, and so the virtual memory subsystem of an operating system, it has mainly two major tasks. One is page selection, the other one is page replacement. Okay, so the page translation is handled by MMU. So that's not something that VM subsystem worries about. But however, when the page fault happens, that means like when the page that is needed by the process is not present in the main memory, then it needs to do page replacement. Okay, and it also needs to know when to bring the pages. Okay, so when to bring the pages, we have actually we looked at the demand paging. However, there are other ways in which operating system can bring the pages that are needed by the process. The first option is pre-paging. Pre-paging is the simplest technique where operating system just fills up the entire uh, virtual address of the process. Basically, it creates all the page table entries and it loads all the pages that are needed by the process into the physical memory. Okay, this is called pre-paging. However, this is inefficient because, as we have seen in the previous class, many pages or may not be used by the process. So it's very inefficient to bring all the pages. However, Windows 10 actually uses a nice trick where when you are running a process in Windows, especially Windows 10 monitors which pages are immediately loaded by the process. Okay, so once it figures out the pages that are immediately loaded by the by the process, then it creates a file called prefetch file, which contains the list of pages that are needed by the process to start. So when you run a program on Windows, it actually looks into prefetch folder to see if there is a prefetch file for that process, for that program. If there is a prefetch file, then it will load all those pages before even they are requested, hoping that these pages will be needed by the process. Okay, Linux doesn't do pre-paging. However, there are some flavors of Linux, maybe SUSE, which have some version of pre-paging implemented, but it's not enabled by default. Like you need to enable this kernel configurations when you're building the kernel. Okay, the second option is request paging. So here, we give the responsibility to the program or the process to request the pages. So the process will request all the pages that are needed. So operating system will only load those pages. Okay, so if the page is not present in the main memory, then operating system just kills the process because it is the responsibility of the process to request the page. Okay, this is called request paging. However, this is very hard to get right because process may not know what pages it may need, right, during execution. So the other approach, the favorite approach, and the approach that we will be seeing throughout this course, and the approach that is used by all the operating systems, it's called demand paging. Here we start the process with no pages. So we will load pages only when the page is absolutely needed by the process. Okay. So we know now we have seen when page replacement happens. Now operating system needs to know which page to replace, right? So it has various choices. It has several physical pages, so it can pick any one of the physical page to replace. So how can operating system select a page to replace? Let's look at an example. So this is the heat map. Consider that there are only 6 pages in the physical memory, and the more brighter, or like the more darker the color means that address is heavily used. Lighter the color is means the page, or like that address is less used. So which page should operating system evict? Right. Any answers? So given this, like this is the usage of the memory pages. Okay, page 4, right? Because it's rarely used. Yeah, that should be the candidate. Okay, what about now? There are perfect. Yeah, there are 3 choices, right? Yeah, 2, 4, and 5. It can replace any one of them. Okay. So based on this observation, okay, so good page replacement policy should reduce page faults. Why? Because let's say what happens if we replace, let's say, page 6 here. Like so if an operating system replaces page 6, then it's a bad thing, right? Because that page is heavily used. So the process that is requiring page 6 might might get page fault immediately. So that's why we should not replace page 6. If that's why we should replace page 4, because page faults doesn't happen. So good page replacement policy should reduce page faults. Very good. So now with this observation, let's create a new page replacement policy. Let's call it Mechery page replacement policy. This is my page replacement policy. So what I do here is I maintain a number called usage number for each physical page. Okay. So whenever a memory access happens, so I record every memory access, and for each memory access, I just update the usage number for that particular page. Okay. Whenever I get a memory access, I get the physical page corresponding to that memory, and then I just update the usage number of that physical page. Okay. So when page fault occurs, or when demand paging, like when demand paging is needed, what I do is I just pick the page with the lowest number, and I get my page from like the disk and put the page back, and I reset the number, like the usage number, to 0. Okay. So what's wrong with this policy? I mean, this for me is an amazing policy, actually. Can anybody see like what's wrong with this policy? Okay, Jacob said poor recency. Okay. Nice. Yeah. Very nice. Exactly. Keeping track of every usage, good luck. No. So the reason for this is, like, imagine even when the page is already present in physical memory, even then we are doing some work. Okay, that's very inefficient. So it's so this is, although this is very good, although this is like reasonably good, the the fact that we need to record each and every memory access just just induces so much overhead that the page replacement policy is like unusable. Okay, and furthermore, like there is poor recency, right? That means future is unpredictable in the sense a page that is heavily used, let's say, if, imagine a page that is heavily used couple of seconds back, but the number is very high, so we just have that number, so we never clear that number, so we don't even take care of recency. Yeah, and the other thing is even if a page is used heavily now, the page may not be used later, so we don't know the future. Okay, but we are making decisions from the past, which is okay, but the main problem is the high overhead. Okay, so good for a good page replacement policy, it should minimize the total number of page faults and it should have minimum latency. Okay, so ideally, in case of page hit, that means when the cases where page is already present in the physical memory, the overhead should be zero. Okay, and latency during page fault should be very minimal, like it should not take so much time. Okay, so these are the two main requirements for a good page replacement policy. So the crux of a good page replacement policy is to find a page that is least useful. Okay, once you find a page that is least useful, then all we need is to swap out the page and swap in the page, that's it. So but this is very hard because we don't know the future. However, in most of the cases, past behavior is a good indication of the future behavior. So we can, like if we can somehow keep track of the past behavior, then we can extrapolate that to be the future behavior. But again, keeping track of past behavior is very hard. As we just saw, like keeping track of every memory reference is like it induces a lot of overhead. Okay? So yes, we should minimize overhead. Most of the page replacement policies, what they do is uh, they try to balance between the overhead and the page faults. Okay, so they try to get imperfect information by using low overhead mechanisms. Okay, with this imperfect information, they try to make some page replacement guesses. Okay, so this provides a good balance between like overhead and performance. So few jargons, like few definitions, or rather few terms that are mainly used during interviews, like pressure means demand for a resource, eviction means throwing something out, page eviction, cache eviction means like throwing a page into the disk. Similarly, cache eviction means uh, clearing the cache line and putting the cache back to the memory. Pollution means bringing useless pages or cache lines into the into cache or page, into the cache or main memory. So trashing is basically useless work done by like page replacement policy. So trashing can happen when we bring you mostly useless pages into the memory, right? So, and locality is a property. Locality means reuse. So programs have both temporal locality and spatial locality. That means programs tend to reuse most of the stuff. Programs tend to reuse within the space. That means programs tends to access data within the same region most of the times. And then programs tend to spend their time mostly programs tends to access the same data again and again. So that is called temporal locality. And spatial locality is when programs try to access data that is adjacent to each other. Okay, I mean, this is kind of intuitive, right? Because most of the programs that we write, like we have sequential structures, like we have arrays, we have lists, like most of them are sequential. And similarly, temporal locality, you can see that most of the times we just update the same variable again and again. We try to access the same like global variable, update the same pointer. So these features of programs, they give rise to locality. So at the processor level, processor usually sees like same instruction being executed again and again. Okay, so so what can we do? Like what kind of page replacement policy we can have without any hardware support? Okay. The good old friend, first in, first out. So here we just maintain a queue of pages that we replaced. Okay, and whenever we need a page, we just take the page frame, like physical page frame from the head of the list, and then we replace that page. Okay, the overhead is very low because we just maintain the queue. And disadvantages of first in, first out is there is no recency, right? We don't care if a page is being recently used. We always take the uh, page which is at the head of the queue, even though it is used recently. Okay. So this could actually, in principle, lead to trashing if you keep on replacing heavily used pages. Okay, another interesting problem with first in, first out is it has a very nice problem where, like, when you increase the, if you're using first in, first out page replacement policy, increasing physical memory could actually make the replacement policy go worse. Okay, so which is counterintuitive, right? So irrespective of whatever page replacement policy you use, increasing physical memory should always decrease the page faults. Whereas in case of FIFO, that's not always the case. Increasing physical memory could actually increase the number of page faults. So this is called Beledi's anomaly. It's because of Lazo Beledi who first detected this. So here it's the anomaly is simple. Like if you use FIFO, then more page faults, like increasing physical memory can increase number of page faults. And this is not always the case. This again, like Beledi's anomaly doesn't happen for every memory access. So this happens only for like certain accesses. Like an example is as shown on the slide. So here, consider that these are the requests for the, like these are the like requests generated by processes that are running, and these are the requests for physical frames. Okay, or like these are the requests for, like consider these are virtual page requests. Okay, so these are the requests made by the process, and where each number indicates the virtual page number. Now consider the case where we have 12 KB of memory divided into 3 pages. We call frames. For physical pages, we call physical frames. So we call frame 1, frame 2, frame 3 are the physical pages. Okay. So top row shows the request for the virtual pages, and the boxes in red shows page faults. So here, when we get request for page 3, since the page 3 is never loaded because of demand paging, so we load page 3 and we put it in frame 1. Next request comes for page 2. We have free frame 2. We put page 2 in frame 2. Similarly, we put page 1 in frame 3. And next, when we get request for page 0, we replace page, we select frame 1 because of FIFO. We select frame 1 to be our victim frame, and we swap page 3 out, and we load page 0 into frame 1, so on and so forth. Right? So here the boxes in red shows page faults. So there are 9 page faults, and the total memory is 12 KB. Okay. Now this is an example where we have 4 frames. That means we have a total memory of 16 KB. Okay, and the same requests. Okay, the request did not change, but the number of page faults is 10. Okay, so this is called Beledi's anomaly. So for a given request, increasing the physical memory can increase the page faults. That means it can make the algorithm worse. So this is what we would expect as we increase the number of frames along x-axis. We should get some inverse exponential curve where the number of page faults decreases. But in case of FIFO, what you actually see is as shown on the slide, like the page faults might increase as we increase the number of frames. Okay, so similar to like shortest job first algorithm in process scheduling, in CPU scheduling. So we have similar algorithm called optimal or min. It's also called Belides algorithm. So this algorithm like gives us the best performance any page replacement policy can ever have. Okay, period. So if somebody can implement this algorithm, that is the best algorithm that you can ever have. That means this gives you the minimal page faults. Okay. Here the logic is simple. Basically, we replace the page that won't be used for the longest time. Okay, that's the algorithm. But this is very good because it provides a guarantee that the number of page faults will be minimal. Right? Like, but the thing is, it's very hard to implement. Why? Because how can we know when the page will be used? Unless process tells us that when it is going to use a page, it's very hard to know whether a page will be used or not in future. So because of this, although theoretically this has very nice guarantees, it's almost impossible to implement this in practice. So we usually use this algorithm as a benchmark, as a comparison benchmark with other page replacement policies. Let's say if you come up with some page replacement policy, the way you can show your page replacement policy to be good is to compare your algorithm with the optimal algorithm and see the number of page faults. Okay. So this is again similar to shortest job first. Similar to there, we also have the guarantee that turnaround time in case of shortest job first will be minimal, but there we need to know the end time for each process, so which is hard to get. So in order to predict future based on past, we can use locality. So one way we can say whether a page will be used in future or not is based on whether it is used recently. Okay, it is used recently and more frequently. So if a page is used recently, most likely the page will be used again in future. Similarly, if a page is used frequently, again, it's most likely the page will be used again, right? So these two are temporal properties, right? Because these two are in time domain. And why don't we care about spatial locality? Because we always deal with single page at a time. So we don't deal with multiple pages. Okay? So we don't care if a process accesses adjacent pages. We only care how frequently does a process accesses a given page. So that's a temporal property. Okay? So based on these two features, if we can somehow record recency and frequency of a page, we can use these to know whether a page will be used or not. So it's very hard to do it in software, because in order to do it in software, we need to record each and every memory access, which again is tedious. So what hardware provides is, in case of x86, they provide a bit called accessed bit, so which will be set by MMU whenever process accesses the page. Okay. So whenever process accesses the page, it just sets the bit. So this way, a page replacement policy can check whether a page is accessed or not. Okay. This is just one bit of information. It doesn't provide frequency, but this can be used to get recency, right? Because if you clear this bit very frequently, then if the bit is always set, then you can know that process is using this page, it has used this page more recently. Right? So we can use that reference bit to improve our good old FIFO algorithm. So here, it's the same FIFO, but when the page fault happens, that means when we have to pick a victim page, we select the page at the front of the queue. However, now we check if the reference bit is 1 for that page. If the reference bit is 1, we just move the page to the front of the queue and we go on, like we go to the next page. Here in this case, for instance, let's say page 15, the reference bit is 1. We move page 15 to the head of the queue. We go to page 1. We again check if the reference bit is 1. If it is 1, we again put the page to the head of the queue. We go back and let's say now we check page 2. If the reference bit is 0, then we select page 2 as the victim page, and then we do our replacement. Okay. So, and when we actually put the page back into the queue, we actually clear the reference bit. Okay. So when we see that page 15 has reference bit 1, we clear the bit and put the page back into the to the head of the queue. Okay. The advantages of this algorithm is fast, because we just need to do 1 bit check for each page. In worst case, we may need to go through all the pages, but depending on the length of the queue you maintain, this could be very fast. Okay. And again, depending on the length of the queue, the algorithm could be really slow. If you maintain the queue length to be, let's say 1024, like 1000 entries, of course, the algorithm will be slow. Yeah, that's it. In the next class, we will look into more page replacement policies, more interesting page replacement policies. So any questions? Okay, I guess that's it. So if you have any, okay, Ragul asked the question, can we change PR policy in Windows? Maybe you can. There must be some registry entry that you go and then you just disable the prefetching in Windows. Yeah. Windows has all the knobs that you ever need. That's why Windows has so many malwares, by the way. Yes. So if you have any questions related to lab 3, or if you need any debugging with lab 3, I'll be open. Like we can open one-on-one session and we can go through your code.
Hi, I had a quick question about Lab 3. I was been running into some difficulties with kind of debugging some strange things. I was the one on Piazza who asked about the illegal instruction.
Oh, okay.
So I've been, do you mind if I share my screen?
Sure. Yeah, let me allow you.